So, okay, I want to be talking about cut edge failure, but it is actually also known as edge cracking. And so we did a micromechanical investigation, and what we see is, depending on how we make a cut, like with blanking or with laser cutting, actually that has a huge influence. Okay, there's some work, actually a bit of a side project that I did with two PhD students of mine, former PhD students. Chow I-do is at the Max Planck Institute of Eisenforschung in Düsseldorf at the moment. Tasan, who went to MPIE but then went to MIT, just recently got permanent position at MIT, so that's nice. So the three of us worked on this a bit, a long process I would say. So we've been looking in general at advanced high-strength steels, together with Tata, they like this. They want to also make, for instance, these kind of crash barriers. Supposedly this material should be good because of high formability and high strength. But then again, if you look at these advanced high-strength steels, at Tata they find all kind of unpredicted failure under complex loading. So the drawing, hamming, dredge boxes and ever tubes. So where is this coming from? So this is some earlier research, 2004, where they did basically looked at two steels that have the same ultimate tensile strength, and clearly steel A should be superior because it has a much larger total elongation. But this has been tested in a uniaxial tensile test, and basically here you're testing for global ductility, so the behavior to resist necking. But you can also do a different type of test, like a hole expansion test. As you create a hole, you come in with a punch, and then at some point a fraction will occur. And that's more like testing the local ductility. And now if you plot the uniform elongation from the tensile test versus the hole expansion ratio, now you see that the steel A has a very good elongation, but the hole expansion ratio is actually pretty bad. So, they have very contrasting material behavior, and this has been repeated a number of times in the literature for every time two steels with the same ultimate tensile test, ultimate tensile strength. Okay, and now if you look at cut edge failure or edge cracking, that's basically this kind of behavior. It's a special case of the mismatch between global and local ductility or formability. So in terms of forming, you would like to have a material that has large formability, so this kind of behavior should be good. But of course there needs to be holes in there, and locally at these holes there's going to be cracking, so you would like to have this kind of behavior to be very good. And so this contrast then really becomes a problem for a company like Tata. Okay, that brought us into this topic. So the idea is we want to do a clean study of cut edge failure to try to understand it a bit better. And we're going to compare two types of ways of making these holes, like blanking and laser cutting. And we can do blanking with a gap of 2.5% to 10%. This is small, this is considered large, so we're basically covering the range. And we're going to do this for a model material. And for advanced high-strength steels, dual phase 600 is a material that we know very well. So first we're going to make these cuts, and we're going to characterize the microstructure in the cut position. And then we're going to do mechanically deforming this, right? That's the whole idea with this cut edge failure. You first create a cut that does something to the material, and then you actually start deforming it. So there's double process, and so we're going to be characterizing. There's a whole range of techniques we applied actually to this. So why do we think dual phase 600 is a model material? Well, first of all, we have a clean dual phase microstructure. So we have these big ferritic grains, and we have these martensite islands. So that's just a two-phase material. And when we deform this, in this case inside the electron microscope, then we see ductile damage. And ductile damage, actually, we've studied quite a bit in literature in general. There's a lot of literature on ductile damage in dual phase steel in general, but also particularly on dual phase 600. We also contributed a bit to this over the years, but this is just not looking at cut edge failure. So the question here is, how does this material behave under cut edge failure conditions? Okay, so first let's look at blanking. So we create a hole and blank, and just look at the cross section here. And the cross section looks like this, but more schematically it looks like this. You can now see a punch coming down, there's a die, and this material is sort of like sheared off. And that leads to this kind of of cut edge. And you can see actually this cut here, so there's a rollover depth. Here, there's a burnish zone that's going from here to here. There's a fracture zone that's going to here, and there's a buckle. So we see all the common features that you would expect. Then we have the shear affected zone. That's basically, if you look at the hardness, it's constant here. This is the bulk region. But from this point onwards, that's the shear affected zone. The hardness goes up. So here in this region, we're affecting, the cutting is actually affecting the material behavior. So the hardness is changed, and the void density also goes up here. So we track that, each individual void and cross section. And we do electron backscatter diffraction on basically this region here. You can see it here. And this is you can see the grains. A bit further away you still see the bulk grains. Closer to the edge, the cut edge, you can see actually grain or rotation and elongation. And now here it becomes dark, and because that's an overlay with image quality, that means that the quality of our diffraction pattern goes down, and that's due to the presence of dislocations. So roughly you can see that the amount of dislocation starts quickly going up towards the cut edge, and that then also relates actually to why we see this hardness going up. Okay, this is just for blanket with 2.5%. We also did this for 10%. This rather looks basically the same, but let's compare it more directly, these two cases. Now the blanket with 2.5%, then the gap is smaller, and we can see it's more shear dominated deformation, what we would expect. And here we get more like a bit more tear dominated deformation, and the fracture zone is also larger compared to this one. Oh, that's not good, sorry. We also see more shear induced work hardening here. That leads actually to a higher hardness compared to and a higher dislocation density in this case. Yet in the 2.5% clearance we get a thinner shear affected zone, 0.3 millimeters versus 0.5. So this is all actually a bit what we expected. And then this corresponds to, because this is more shear dominated, we get a cleaner fracture surface. And this is more tear dominated, this one, and we get a zoom in here, you can actually see that it becomes rougher, more defected zone, fracture area here. And if you look at literature, then this really corresponds, because you would really expect a clean coalescence of small voids and narrow shear bands in this case, versus more void growth and wider tearing band for when you have a larger clearance. So this dual phase steel is actually behaving as we expect, but we should say actually that both cases they show a more like shear dominated deformation. And instead, comparing to other materials, it could be much more tear dominated than what we see even for 10%. Right. So in general, we see actually quite low void density. You can see it here, the little speckles here. It does go up here, but not too much. Okay, and now let's look at when we make a cut with laser cutting. Now, we have basically the same measurements that we did, but if you now look at the image quality of EBSD, now you can see that, well, it's becoming darker here, but it's not exactly dark, so you can still see it, it's better. So it's a cleaner microstructure. That means a lower dislocation density close to the surface, and also the void density is actually not going up at all. It's just the same as in the bulk. And if you now look at the hardness, in this case we have a heat affected zone, then it is a microstructure zone with very different mechanical behavior. So then now you can see really a plateau, it's not just shooting up. And of course, in order to understand this, then you really need to look at this laser cutting process, because they're basically locally melting this. So very close to the cut edge, it saw the melting temperature. Further away, it saw a lower and lower and lower temperature. And that then we can relate to each of the positions of the cut edge to what kind of temperature saw up to the point where we have the bulk material. So if you relate this to the thermodynamical phase diagram, you can see that here it went up to a high temperature and we get a rapid quenching, so we get full martensite. Here we get a more intercritical annealing range, so we can still have some full martensite in there, but only partial. And this is a regime that looks, in terms of microstructure, the same as the bulk, but this is a tempered region. We tested this you can see that from the hardness. Okay, this is just the starting position basically for a good edge failure. Now we start mechanically loading this. Now, what kind of mechanical test should we do? We can do hole expansion test, but that's actually a really ill-defined test because of the contact that it's very poorly known, and it's also not very representative for failure in industry. The way it's being loaded, and in-situ microscopy is very difficult. So what we do, we have what you call a Marciniak test. Marciniak was a clever guy, so we have this setup, but we designed it that we can do this inside the scanning electron microscope. That's nice, and in this case we sort of like misuse this device to test these discs with a circular cut, like a circular cut hole, and we biaxially stretch this. So we just let the material decide itself where it wants to fit. Now, the nice thing is we can do this inside the SEM, but also inside the optical microscope. We have no contact at the whole edge, so we're not touching this. Even the punch is never directly touching this because there's a washer underneath. So it's all like a floating, it's biaxially being stretched, while we can do these in-situ tests. Okay. So in optical microscopy, we can do digital image correlation around the hole, and here you see actually the strains, the strain map, and here you see a correlation coefficient map. It turned out that when you have some damage, the correlation coefficient immediately drops down, so it's a very nice indicator of where basically damage starts occurring. And we can do this, of course, for blanking with 2.5% clearance and 10% clearance. So we get these strain values, and we plot them as a function of crack length, so from this point on, the crack starts initiating and it starts shooting up, and these 2 points are the points where we see the first damage occur. Okay, what can we see compared to these two clearances? We see that there's a rather homogeneous deformation in the 2.5% clearance. You can see here. First, a strong localization that triggers early failure in 10%. If you look at SEM, then So all of the D, E, F, and G, they correspond with these positions here. And then we can see that for the 2.5% clearance, we get consistent failure behavior. The first micro damage becomes the first micro crack. But at the 10% is also unexpected failure behavior. So the first micro damage is actually not the one that will actually be the final crack. Okay. So that's interesting, but it becomes more interesting when we start comparing this with the laser cut specimen that we now biaxially stretch. First of all, you can immediately see that this crack starts propagating at a much larger strain, equivalent strain. So there's clearly a higher crack growth resistance. And also, if you look at the strain, this is the strain field, but specifically this correlation coefficient, even at the point when we're here, then at the moment the crack starts forming, it's still, the correlation is still very good. So it means there's very homogeneous deformation at the smaller scale going on. So the digital image correlation is still able to capture this. And now if we look in detail, we can see here there's number D, E, and F here. We can see the damage, and then at some point we get the initial crack, we get the crack really propagating. But if you look at this point, this is the point of first damage that we can observe. Now where would this be here, right? Well, you would think that because the crack would propagate at a much later state, that there's also this initial point of damage would also be somewhere on the right. Oh, but look at this, it's completely on the left. So the first damage that we're seeing is happening much earlier than in the case of blanking. But the crack actually, it takes a huge amount of strain to actually get this crack propagated. So, it is consistent. This first damage actually evolves into a major damage, into the first crack, into a crack propagation. That's basically here outside of the screen. But there must be a toughening mechanism at play, right? Like what's happening there? Now, well, this of course has to do with all these different microstructures. So this first damage, that occurs exactly in the zone where we have the fully martensitic layer. And so that actually damages very easily. But then if you look at then in time, then the damage develops, but it really is being arrested. And the reason is that we have this very tough layer here. That's a tempered martensite. So the full martensite, that's really region A and B, early micro crack. And then we just have a very gradual damage propagation into zone E with the tempered martensite, and that's really the tough layer. And there it really gets stuck for some time, get a crack arrest. And that really explains why there's such a big difference. So because we have these different, so in comparison with the bulk material, the tough layer actually here helps really a lot. So we created basically this protective layer by doing laser cutting. So can we further improve cut edge failure with the gained insight? Well, we know that if you do blanking, then you induce damage. Work hardening, well, that's bad. We know that if you do laser cutting, you have these initial layer A and B, and that's also bad. But we like the tough layer here. And on the other hand, laser cutting is also it's expensive. So it is being used in industry, but mostly blanking is being used much more on that because it's much cheaper. So the solution that from this, what we reach is we should actually do hot blanking. So hot blanking basically at a temperature that actually induces this kind of toughening mechanism. And because of that high temperature, we will also induce less deformation and damage into the material. And this is something that I'm now trying out. I can't say anything about this. Yeah. Okay, that's our suggestion, and that should be, yeah, okay. Now this is basically the work. It's, by the way, we presented this in the scripta paper. So it was kind of nice wrap-up of that material, but that didn't exactly explain what was now explain the paradox between the good and the local and the global ductility, basically. And that is something we're now also, but it's another presentation, we're studying actually with numerical methods, where we're doing statistical evaluation, so of all micromechanical studies. So we're introducing into the microstructure different damage size, and we're looking actually what's happening. So if you want to know more about that part, you'll have to approach me directly after this. So with that, I'll leave it. Thank you for your attention.
Thank you, very interesting. Questions at the back?
Thank you for the nice presentation. I have a question on the blanking EBSD map that you showed, the IPF and the image quality map. So there you say that you have dislocations, that's why your image quality goes down. But won't you expect, like if you have dislocations due to blanking, you will have some amount of low angle grain boundaries which you can resolve with EBSD actually. You will have some amount of low angle grain boundary statistics coming there.
Yeah, so the very clean dislocation walls, typically, like if you do some cyclic loading, then the dislocation starts rearranging them in walls, and internally the EBSD quality is sort of like recovered a bit. But if you do a one-time deformation, and typically you don't see this immediately, that you get these long-range formations, structures that you get from the dislocation structures. So basically the dislocations are everywhere, and it's just generally decreasing the EBSD quality. So that's something we've also seen if you do monotonic loading for steels, also other metals. So I'm not completely not surprised that we see this kind of behavior. So but it is of course very indirect, because basically the quality here is we looked actually, I didn't say this, but the surface preparation we use even broad iron beam milling for this, so the best way. So it's not induced by maybe rounding off due to grinding and polishing or anything. There was no way you could get image quality better. So very close to this cut edge, if you just look at the EBSD quality, even though it's very flat, but the EBSD quality is very poor. And the only So like a logical reason would be that is really related to the dislocation density. It's also not that the grains are so small, and this looks maybe small.
50 microns, so.
This is 50 microns, right? So like they're still large enough, right? The interaction volume for EBT is about 50 nanometers.
Yeah.
So that we're talking about a factor of 1,000 difference still.
What was the step size used here for EBT?
Yeah, well, for this large, I don't know, but it will be quite large. But also we did some scans actually at the surface with small step size, and the image quality didn't improve. So it's not, even if you would have large step size, you might hit, for instance, of course, sometimes the grain boundary or something, but you would also be regularly hitting basically the internal areas of the grains, and we didn't see, So we did quite some check.
Like quantify the dislocation density in blanking versus the setting using
Sorry?
Would you quantify the dislocation density using XRD or something from blanking or laser cutting in this area, because then it would relate that to the problem?
Yeah, maybe you need to do it locally at the edge that could also be possible. But to be honest, that was not really the goal. It also nicely aligns with the fact that the hardness went up. All of basically the measurements that we did basically showed enough for us.
Yeah.
But yeah, we definitely can always study this in more detail. But thank you.
Thank you.
Firstly, thanks for the super interesting presentation. What I'm curious is this whole talk or the process between blanking and laser cutting is more towards how the forming process itself. But now my question is, like, now we have a blank specimen and a laser cut specimen. Now it is in service, like for example, it's a hydrogen like this. And when there's a laser cutting and there is probably local melting and martensite transformation plus carbide formation at the boundaries, we can expect some residual stresses. So could you comment anything on this?
Yeah, in service, and then like what kind of loading in service? Also like some fatigue loading with hydrogen embrittlement. I don't know. I don't know if I dare to say anything on that. Yeah, I would still expect that I would be surprised. The effect that we found with this tempered layer, that was the sort of like that gives the toughening effect. I would still expect that that's going to be important. I think it is known also for maybe something unrelated, but maybe not. We were working together with a company making scissors for a fire brigade. So these are basically quenched, also fully martensitic steels, and they were, because of these advanced high strength steels that the steel companies are producing now, so now they need to cut stronger steels, right? So they also, the fully martensitic, suddenly these scissors start actually fracturing. They're supposed to last 1,000 cuts or something, and after 3 cuts, some of them already fractured. And so what we ended up doing is changing the heat treatment and giving a tough layer. So also at that time, some lessons learned, and that solved the complete problem. So I'm not saying it's the same situation, but that's also like maybe low cycle fatigue, and there's no hydrogen embrittlement involved, and I don't dare to say anything in relation to hydrogen embrittlement. Sorry.
I was just curious because I never thought that there could be such a significant difference between blanking and laser cutting.
But it is, also from other examples, it is known if you can create a tough layer at the surface, you can really improve actually the material. So, and that's why I come with the example also with the scissors, that I was involved in that myself, but I know there's some studies also in literature where in different applications they've seen that. So, yeah. Okay, thank you.
Okay, I think with this we can conclude the session. Thank you, Johan, again.